Welcome, everybody. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to have all of you in another session of the Logicians in Quarantine seminar. It's a pleasure to introduce you Professor Johanna Franklin, who kindly accepted our invitation to give a talk, and we'll talk about computability theory. Johanna, thank you very much, and it's up to you.
Thank you. It's a pleasure to be speaking. Well, I would normally say here, except, well, I've been spending every day in this room for the past 4 months, but I hope that sometime I can visit and give a proper talk in person when it's safe for me to do so. So I'm going to be talking.
It will be a pleasure to have you here.
and I hope sometime to host you in New York. So, okay, so I'm going to be talking about randomness and computability theory. And randomness is the sort of thing that most people feel that, you know, we all have some sort of intuitive definition of randomness in our heads. But as mathematicians, you know, we'd like to have some formal definition to be able to say this is definitely random, this is definitely not random. And I'm going to talk about how computability theory gives us the framework to actually classify something as random or as not random. So, onwards, I'm going to start out with something that lets us talk about our intuitions after, of course, the outline. I suppose I should have put here the preliminary talk about intuitions a little bit. But then I'll discuss the tools of computability theory that are necessary to formalize randomness and make it a more precise notion. I'll talk about different approaches that people take to defining randomness. Then I'll give some basic facts about random objects. And then I'll present some of the kinds of questions that people might ask about randomness in general. So, let's start with this. Which of these sequences look random or looks random, and why? So, you know, at the top we see something that looks like all zeros. Then the next two have some ones and some zeros mixed in together. Would anyone like to suggest which of them might definitely look more random than the others, or which of them you would say that's not random at all? Don't make me do all the work. No? All right, well.
All of them may be random, depending on where you are.
That's okay. So the point is that perhaps we can't see past these 3 dots at the end of each one, right? It's possible that this one that looks very regular at the beginning becomes very irregular later on. It's possible that this one becomes all ones after this point, or maybe after you see the first 100. We don't know, but suppose that they all go on roughly as they are. With any pattern you can detect, that would continue to exist. Any pattern you can't detect, you would continue to not be able to detect the pattern. So I've shown this example enough that I think I can probably speak for at least most of the audience. I think most people would say that this first one doesn't look random. It's all zeros. You know exactly what's going to happen at any point in the future if it continues on in the same sort of way. The next one is somewhat more complicated. You have 0, 1, 0, 1, 0, 1 over and over and over again. And you could tell me exactly what's going to happen anywhere. It's very predictable. And then this last one, well, if any of them are random, it's probably this. Because what do you see? You see 2 zeros, a single 1, 2 zeros, a single 1, 4 zeros, let me go through and count, 6 ones, 1 0, 2 ones, so on and so forth. And there's not a detectable pattern for this as it is for the others. Unless, of course, you are used to taking all of your fractions and translating them into binary, because it turns out that if I put a decimal place here, although I would really mean a binary place, so this would be the halves place and the quarters place and 1/8 place and 16 and 32nd. So this number would be 1/8 plus 1/64 plus whatever this would turn out to be. If you do all that, then if you take that 1/8 plus 1/64 and so on and so forth, what you get is something that looks like the decimal part of pi. So now maybe we should ask if pi should be considered random. And it's certainly tempting to say, well, it's far more random than either of the first two. But I think that I'm going to argue that pi is also not random. Because think about why you might say that this first sequence here is random. You might say that is not random. You might say that it's not random because it's very predictable. You know exactly what will happen at any place. Well, pi, you can calculate and you can know exactly what the, say, 100th bit of a binary expansion of pi would look like. You might say, well, I could write an algorithm that would generate this sequence or this sequence. But as we tell our calculus students, you can also write an algorithm that will generate pi. So I would argue that pi isn't random because it's as predictable as the other two. It's easy to describe. You could write a very short computer program that would give you the nth bit of pi for whatever n you want. And furthermore, it's easy to identify. That's the last method I'll use to describe it. But the point I want to make is that pi is every bit as non-random as a sequence of all zeros. So now let me maybe try to make that more formal and talk about the tools I'll need to do so. So in our universe, and this is just the standard notation part of any talk, I'll talk about an infinite binary sequence, and I'll call that something like A or B. If I want to talk about a finite binary string, I'll talk about sigma or tau or some other lowercase Greek letter. And I'll also say that the only things that I would consider random are infinite in some way. And that's because if it's finite, I can tell you exactly what it is in a finite amount of time just by listing off all of the components of it. And if I can describe something precisely, I don't want to say that it's random. Okay, so infinite binary sequences, finite binary strings. This is something I tend to be very careful about. If I want to call something infinite, I will use the word sequence. If I want to call something finite, I will use the word string. Okay, the other thing I might want to talk about is all infinite binary sequences that start out in a certain way. So I would use those square brackets to say, well, everything that starts like this. So if my sigma in those square brackets is 0, 1, I'm saying I want all of the infinite binary sequences whose first two bits are 0 and 1 in that order. I might also want to be able to talk about the first, say, k bits of any infinite binary sequence, or a finite binary string even. I might want to be able to say a finite binary string is this long. In that case, I'll indicate its length by using the bars. And I'm also going to want to talk about measure in some way. And in this case, I'm going to use the Lebesgue measure on the Cantor space. And the basic open sets are these, are given by, say, the initial segment of the binary sequences in that case. So the measure of all of the strings that start with, say, 0, 1 will be 2 to the minus 2. And that makes some sense because 1/4 of all strings begin with 0, 1. Okay, so that's the notation. Now let me talk about the tools I'll use. So this is where the computability theory comes in. So my basic tool is going to be a Turing machine that may not always give an answer. I'm just probably going to keep saying computer program because that's more intuitive for most of us these days. Very few of us are accustomed to programming a Turing machine. And we're far more accustomed to programming in, I don't know what people learn these days, Java, Python, C++, ML, assembly, whatever you happen to like. And as we know, at least from our early days of programming, a computer program might not give an answer based on every input. However, there are some special ones that do, and a computable function is just going to be a total function that's defined by a Turing machine or that you can write down as a computer program. So a function that gives an answer whatever the input. And in general, I think of the input as being an integer, positive integer, well, non-negative integer. But I could use any other computable set as my inputs as long as I have a way of coding them as non-negative integers. So for instance, I could take as input, say, a finite binary string. There are countably many of those, and there's a very natural way of coding those finite binary strings via integers. Okay. Or I could use rationals as my input if I chose to do so. All right. So basically, I'll use computable functions the most often. Think of it as a computer program that will give you an answer no matter what input you use. The other kind of tool I'm going to need is a computably enumerable set, a CE set. And this is a subset of the natural numbers that is the range of a computable function or the empty set itself. And the reason we might call those computably enumerable is that you can use the computable function to enumerate them. You have your computable function f, you find out that f of 0 is 12, and you know 12 goes into your set. F of 1 is 6, so 6 goes into the set. F of 2 is 35, and 35 goes into the set. So you can enumerate all of the elements of your set as you go, but keep in mind that this will only give you positive information because you are enumerating the objects in your set, but there's never a point where if, say, 42 hasn't gone into the set yet, you really shouldn't just say, well, I haven't seen 42 go in. I've checked all of the inputs from 0 up to 1 million. I haven't gotten 42 yet. Therefore, 42 is not in the set. Because I can tell you what will happen in that case if you are very unlucky, which is that when you put 1,000,001 in as your input, you will get 42. And you will have been wrong when you said 42 was not in your set. So a computably enumerable set is one that if an object belongs to it, you eventually find out. If it doesn't belong to it, you should never be willing to swear that it isn't in it. So those are the basic objects I'm going to need to talk about: computable functions, computably enumerable sets, and there's one more term that comes more from computable analysis. I might want to talk about a real number that's approximable from below as one that a computer program, well, real numbers are infinite objects, so a computer program can't really output an infinite object. But it could generate an increasing sequence of rationals that converges to it. So for instance, pi is approximable from below because the computer program could first give you 3, 3.1, 3.14, 3.141, and so on and so forth. Okay. So I think this is really all we're going to need. So let me talk about the first way to discuss randomness And I'm going to go back to the predictability approach. Because when we began talking about, well, why isn't a string of all zeros random? One of the things you could say is, I know exactly what's coming up every time. I know what the 5th bit is going to be. I know what the 75th bit is going to be. I know what the 100th bit is going to be. And that was also one of my arguments for why pi shouldn't be random, because I can predict what the nth bit will be for all n. So how do we formalize this mathematically? Well, I'm going to take a function that takes as input a finite binary string and outputs a non-negative real number. And a function like this is a martingale if essentially it gives you some sort of fair betting strategy. So its value at sigma is equal to the average of its values at the string that you get when you extend sigma by 0 and the string you get when you extend sigma by 1. So maybe as an example, d at the string sigma, the value of d at sigma is, say, 2. And let's imagine that you bet, say, 0.5 that your next bit is a 0. Then d of sigma 0 will be 2.5 because you would get that extra 0.5. And d of sigma 1 would be 1.5 because you would lose that 0.5. And if you add up 2.5 and 1.5, you get 4, divide by 2, and you get the original 2 back. So you could think of this as the amount you have after you place a bet according to this function. And it's a fair bet where if you bet 50 cents on one outcome, if you actually do have that outcome happen, you gain that 50 cents. If it doesn't, you lose the 50 cents. It's not like a casino where maybe you might bet 50 cents and get that 50 cents if you're right, but really you lose 52 cents if you're wrong, something like that. This is absolutely fair. But if I just talk about martingales, I haven't said anything about computability. This is just a generic function. I'm not saying it's computable. I'm not saying it's total. I'm not saying anything else about it. Well, I could call a martingale computably enumerable, like I did for a computably enumerable set, if its values are approximable from below. So for instance, maybe at this point I have an approximation for d of sigma. My approximation is that it's 1. And I'm also building approximations to d of sigma 0 and d of sigma 1. And I know that this equality will truly hold, but I only have approximations to that equality at any point in time. But what this means is that a computer can get better and better estimates as I go along. It's turned, making a martingale CE has now turned this concept of a martingale into something that your computer could actually do. You could program this martingale into your computer in some way. So how do we use this to define randomness? Well, if something is random, it shouldn't be entirely predictable. So we say that an infinite binary sequence A is random if for every computably enumerable martingale, well, a certain sequence is bounded. What is this sequence? I ask how much money you have, the value of the martingale, after it bets on the first bit of A, after it bets on the first 2 bits of A, on the first 3 bits of A, and so on and so forth. And if there's some sort of upper limit on those, I say that A is random because it means that there is no computably enumerable martingale that can predict A well enough to make unboundedly much money on it. You might be able to make some money on it. For instance, maybe your martingale will always bet everything that you have a 0 for the first 20 bits. that's something a martingale could do. It would say, you know, I start out with $1, and then I bet that I will bet everything on 0. So if I come up with 0, I get $2. If I get 0, 0, I get $4. If I bet 0, 0, 0, I have 8. And it's possible to have a random sequence that starts out with 100 zeros. And then it becomes very irregular and difficult to predict. But in the meantime, what you've done is you've made a lot of money. So you can't say that it's random if you never make any money, because you're probably going to make some. But you can't make arbitrarily much. There's going to be some limit. It might be a very high limit, but there will be a limit. And you won't be able to go beyond that. So it's random if it's not predictable enough for essentially a computer betting strategy to make a lot of money on it, or at least arbitrarily much. So maybe an example would be helpful here. I claim that if a sequence is 0 at all odd-numbered places, it can't be random. So I wonder if we can come up with an algorithm for our betting strategy that would show us that any sequence that is 0 at the first place, the third place, the fifth place, and so on, could we come up with a betting strategy that would show that you could make as much money as you wanted betting on one of those? I think we can. So you start with $1, and on the odd bits, you bet everything you've got that you have a 0. And on the even bits, you just refuse to bet, because a bet of 0 still counts as a bet. There's no reason, if we go back to this definition of a martingale, there's no reason that d sigma 0 and d sigma 1 can't both just be d sigma. So maybe you refuse to commit at the even places. So I have a question. No, I think probably that's not. Annotating these never works as well as I would like, so I think I'm not going to do it. But imagine that you start with $1 and you bet that the first bit is a 0. Well, if it is, congratulations, now you have $2. If not, then you don't have the kind of sequence you wanted to start with. And then you don't bet anything at all on the second bit, so you still have $2, whether you have 0, 0 or 0, 1. And then for the third bit, you bet everything that you have a 0 again. So if you have 0, 0, 0, now you have 4. If you have 0, 1, 0, again you have 4. And if it turned out to be a 1, well, you've lost everything, but that's not a sequence of the kind that we wanted in the first place. So you can see that every time I get to a new odd-numbered place, I double the amount of money I have. And that means that if I just bet longer and longer, I can get any arbitrary amount of money I want. And we have a non-random sequence, because I can sit here and tell my computer, bet until I have $1 million. And the computer will do it and come back and tell me they did it. And I can say, well, that's not enough today. Tell me I have 3 million. Keep going. And it will be able to do it. So but if I had a random sequence, I couldn't be that greedy. Okay, so that's the predictability paradigm. You talk about a martingale. You talk about a martingale that specifically a computer could handle. And then you say, could a martingale that a computer could have programmed into it could such a program make arbitrarily much money? And if the answer is yes, it's not random. If it's no, then you do have something random. Okay, so maybe another paradigm, another example here. We could try measuring the complexity of a sequence. And here, if I talk about a machine, and this is just the way the terminology developed in the area over time, people refer to machines as essentially computer programs whose inputs and outputs are finite binary strings and whose domains are prefix-free. And what that means is that you can't have your machine be total, for instance, because if it gives you an output for 0, 1, it won't give you an output for 0 because 0 is a prefix of 0, 1, and it won't give you an output for 0, 1, 1, 1, 1, 0 because 0, 1 is a prefix of that. And we can use these to measure the complexity of finite binary strings. So for those people who are familiar with this, I'm talking about prefix-free Kolmogorov complexity. And here we say that the complexity that a machine M gives to a string sigma is the shortest tau, rather the length of the shortest tau, that when you put tau into M, you get sigma as your output. So you can think about sigma as the thing you're looking for, and tau as this description of sigma. And M is what translates the description into sigma. So basically, something has lower complexity if you don't have to say very much to get it back. Think about it as trying to find a friend at a conference back in the days when we could go to conferences, and saying, has anyone seen this person? This is what their hair is like. This is what their eyes are like. They're probably wearing this kind of clothes. And that person has low complexity if you don't have to say very much before someone says, oh yes, they're over there by the coffee. If you have to keep going and keep describing their clothes and keep describing their hair and maybe the sort of bag they're carrying, then that person has very high complexity because you've had to have a very long input to get the output of that person. Okay, so how do we use this to define randomness in a formal way? Well, if we're going to do this, we are going to say that if something has low complexity, maybe it shouldn't be random. Because, say, a string of all zeros has very low complexity. Because if I want to say, describe a string of 100 zeros, I can do that in a very short way. I say, write down a 0 100 times. It's a very simple for loop. For pi, it's more complicated, but I could still do it in a relatively short computer program. I could say to, approximate it to this level and write down those strings. And that's a very short computer program. Well, it's pretty short. But the thing is that you have to consider that it has to be short compared to any input you want to put in. So if I want the millionth bit of pi, I still have that one not terribly complicated computer program. But if something is random, the best you could do, well, there shouldn't be a computer program to make guesses about it. What the best you could do with that would be to say, well, the first bit is a 0, the second bit is a 1, the third bit is a 0, the fourth bit is a 0, the fifth bit is a 0. The next bit is a 1, the bit after that is a 1. If it's random, there's no shortcut or not much of one. You really have to just say each bit as you get to it, which means that the complexity of something that's of an initial segment of a random really should just be the length of that thing. Because if the best you can do to get, say, the first, 100 bits is to list out those 100 bits, there is no shortcut. The complexity of that first 100 bits should be about 100. So that's what we do again. We say formally that something is random if for every machine M makes the initial segments of A look complicated. So the complexity of A, the first n bits of A, should be very close to n. It doesn't have to be exactly n. It could be a little bit smaller. And that's because it's possible to have something that's random, where, say, the first, 100 bits would be very easy to describe. So maybe you could compress it a little bit. You could say something like, well, you start by writing a 0 100 times. And then you write down a 1, and then you write down a 2, not a 2, heavens. Then you write down a 0, then you write down another 0, then you write a 1, then you write a 1. So you got some compression by being able to say the first 100 bits are 0. So that's where that C comes in. You're allowed a little bit of compression, but only a very fixed amount of it. Okay, so now we have a second definition of randomness. Let's look at some example. I'm not going to use exactly the same one I used last time. Oh, I meant to have a pause here, but whatever. So I'm going to say that the sequence that's always 0 is not random. And this is something that I think we probably all believe should be true. If not, I desperately want to talk to you after this. So what I am going to do is I have to show, let's go back, something is random if for every machine I can find a constant such that the complexity of the first n bits of my sequence is at least n minus whatever fixed constant. So what I need to do to show that something's not random is to produce some machine such that there's no constant bound on how far below n you can go. So here we go. I'm going to define my machine. And remember, these machines take as input finite binary strings. They have as output finite binary strings. So I'm going to say that I want to map a string of n zeros followed by a 1 to a string of 2n plus 1 zeros. And I will do that for every n. Well, what does that give me? First, I'll note this is a prefix-free machine. It's certainly computable. It's prefix-free because all of the inputs will have some fixed length of zeros followed by a 1, and there's not going to be any overlap, so we're getting 0, 1, 0, 1, 0, 1, so on and so forth. It's prefix-free. Now let's look at whether a string of all zeros should be random here. Well, I look at what is the complexity of a string of 2n plus 1 zeros. Well, that's going to be n plus 1 because I mapped a string of length n plus 1 to that string of zeros. Well, what is n plus 1? I'm going to do a little bit of algebra and say that n plus 1 is really 2n plus 1 minus n. So what does this mean? It means that the difference between the complexity of a string of 2n plus 1 zeros and its length gets bigger and bigger as n increases. So there's no constant that can serve as the bound. You don't have length minus a constant, and always above that. The actual difference will be a length minus some increasing number. So this is just my argument that this sequence shouldn't be random. All right, so that's two perspectives on randomness, and I think they're maybe the two most intuitive here. The first one, you're saying, well, if it's random, I shouldn't be able to guess what it is very successfully. This one, I'm saying, well, I should be able to describe it taking shortcuts if it's not random, and I shouldn't be able to take very much of a shortcut if it is. Well, there's another way. I promised you 3 ways in the outline, right? The last one is statistical tests, and that is the one that I've never heard anyone really guess if they aren't statisticians. And studying randomness and being the person who teaches upper division statistics in my department probably makes me a very peculiar statistics professor. So let's talk about a statistical approach. Imagine you're doing a hypothesis test. And maybe you choose alpha equals 0.05, as you often do if you're in the sciences. I think that my science students like taking my statistics class just because sometimes they get to use an alpha for a hypothesis test that is not 0.05. So you say, okay, well, alpha equals 0.05. I'm going to say that if we're doing statistics, we might say, I discard the null hypothesis if my data comes out to be in this class of size 0.05. Or you could say, but I want to be really sure that my data is very far away from normal. I'm going to insist that I also discard it when alpha equals 0.01. And then you say, no, it might still be just a little bit normal. I'm going to say that I should reject the null hypothesis if my data comes out to a number that is within alpha equals 0.000001. Well, this is the approach that we have to take when we define randomness in this way. We have to say that a sequence is random if no matter what alpha you choose, then that if you choose a small enough alpha, eventually you can't identify your sequence anymore with it. So this is the first kind of randomness I'm using that has a person's name on it. All of these approaches were determined back in the 1960s, perhaps, let's say 1960s. The history of the subject is a somewhat complicated one that leaves me reluctant to attach names to most of these other approaches, but this one is clearly Martin-Löf. So a Martin-Löf test is a sequence of sets of infinite binary sequences produced by a computable function such that the measure of the ith set is no more than 2 to the minus I. So these sequences shrink. And how does this computable function work? Well, it takes in an input I, and it starts generating a CE set of finite binary strings for that I. So for instance, the I will be the set of all A, such that in the CE set that you got when you said, I want the ith CE set, if one of those initial segments, my sigma 1, sigma 2, is an initial segment of A. So for instance, if I want to get V1, my sigma 1 might be 0, 0, 1, and I will say, oh, anything that extends 0, 0, 1 and then goes on in some way, that goes into V1. And of course, that is only 1/8. And if it's V1, I'm allowed a total of 1/2 measure, so I still have 3/8 to play with. Okay. So now we're going to say, well, how we define randomness in this way. And we'll say that a sequence is random if it's not in the intersection of any Martin-Löf test. So what that means is that I talked about the decreasing sequence of alphas. You want to say, okay, well, I want to discard the null hypothesis at essentially every possible value of alpha. That's essentially describing something that's, this is going to sound very strange, not random. So essentially, it's something that we can't identify very effectively. We can't trap it. So we can't say, my sequence A, it's within this half, and it's within this quarter, and it's within this eighth, and it's within this 16th. If you can focus in like that arbitrarily much on your A, then it's not random because you can chase it very effectively. And maybe if something is random, maybe it belongs to your first V1 and it belongs to the V2, but then not the V3 or not anything else. So something is random if you can't chase it and capture it in as small a class as you want using this kind of CE set as you go. So an example, I'll use the same one. If you're 0 at all odd-numbered places, you aren't random, and that's because I can catch any sequence that is 0 at all odd-numbered places. So what is V1? V1 is everything that starts with a 0, and that has measure 1/2, so that's a good V1. Well, what about V2? V2 is everything where the first bit and the third bit are both 0, so it starts out 0, 0, 0, or it starts out 0, 1, 0. And what's the measure of that? 1/8 plus 1/8. That's 1/4. I'm allowed 1/4 in V2. And then in V3, you can see what I'm doing. In V3, I insist that places 1, 3, and 5 are all 0. So I look at the possible measures of those, and each of those has measure 1/32. So 4 times 1/32 is 1/8. That's what I'm allowed for V3. So essentially at each stage, I'm throwing out half of the terms from the previous stage by specifying one more bit. And if you are 0 at all odd-numbered places, you will belong to V1 and V2 and V3 and V4 and so on and so forth. So I have now caught you using a Martin-Luft test, and you're not random. All right, so now we have these 3 different methods for defining something to be random. You would ask if they all define the same class of sequences, and the answer is yes. And that's one of the things that makes this worth studying. This is a very robust notion of randomness, because it turns out that you can describe the same class of sequences using any of these 3 approaches. They're all fairly straightforward, I suppose, to define. I think I defined 3 computability terms. So all of these methods give you the same class of sequences. That kind of suggests this is worth studying. And these are called the Martin-Luft random sequences. If you don't like naming things after people, you might call it the one-random sequences. Does that suggest that there are 2 random sequences? Yes, it does. And I'll also point out right now that there are other kinds of randomness. So you could require that the measure of the ith set in a Martin-Luft test actually equal 2 to the minus I instead of just being less than or equal to it. And that would give you a different kind of randomness. So you would only use tests where the measures were actually equal, as big as they could possibly be allowed to be in Martin-Luft's definition, instead of less than or equal to that maximum. That's called Schnorr randomness. And it's a weaker kind of randomness. There are more sequences that are Schnorr random than Martin-Luft. And that's because you have to pass fewer tests to be Schnorr random. So if you don't have to pass all of the Martin-Luft tests, you only have to pass the ones that have equality there, then you end up with a larger category of sequences that satisfy it, because it's less work to pass fewer tests. There are also stronger types of randomness, so on and so forth. So I feel like at this point, what should I do? Well, one of the things that people might ask is, well, can you show us a random sequence? And then, well, oddly enough, then sometimes people think, well, if she could show us a random sequence, that doesn't make sense because it wouldn't be very random. But let me show you at least the, not bit by bit, but a construction for a random sequence. And to do that, we need the notion of a universal machine. We have universal Turing machines. We also have universal machines in the sense of Kolmogorov complexity. So we list all of our prefix-free machines, and we define a single universal machine that essentially just copies down each one, but it copies down each one on a separate, essentially, branch of a tree. So you put M1 as 1, 0, and then you basically put M1 above that. For M2, you have 1, 1, 0, and then you put M2 above that. This maintains the prefix-free nature of the domain, even when you combine the domains. So basically, U will give M1, the machine U will give a complexity of n plus 2 to the things that M1 would give a complexity of n2, because the input you need for U is just 2 longer than the input you would use for M1. So it does the same thing as each of those up to a constant, but since we allow ourselves to be off by a constant in the first place, in the definition of randomness, that's okay. And I'll just point out 2 things about a machine U. If you sum up over all of the sigma in the domain of U, 2 to the minus length of sigma, that's approximable from below. Because how would you approximate it? You would say, well, okay, if I input this, do I get an output? If I input this, do I get an output? If I input this, do I get an output? And you interleave all these computations. And it turns out that if the answer is yes, then okay, sigma is now in the domain of U. And I add 2 to the minus length of sigma to my ongoing sum. And what that means is that now I have a slightly better approximation. And it's always going to be a little bit too small because there will always be something else that hasn't converged yet. But it's still approximating from below in a computable way. And I will also say that that number has to be no bigger than 1. And that's just because the domain is prefix-free. You're working on the Cantor space, you're working on a probability space. If the domain is prefix-free, then you can't sum up to anything bigger than 1. And it turns out that that number that I've been looking at, 2 to the negative length of sigma for all sigma in the domain of this universal machine, that's random. So here we have a very strong connection between this universal machine and randomness. And this would be called Chaitin's omega. That's the other name that tends to get attached to other concepts in this area from this time period. It's somewhat misleading to talk about Chaitin's omega as a singular number because that indicates that there's really only one way of coding a universal machine. There are lots of different ways of coding it, but all of them have some of the same basic properties. So it's easy enough to just say anything in this family of numbers you could refer to as Chaitin's omega, and every number in this family will be random and will also have some other particular properties. So maybe now let me talk very briefly about the kinds of questions that people have historically asked about random sequences. Because once you have a new notion, you want to start proving things about it. And if you can't prove anything about it, probably this isn't a good notion. So maybe the first kind would be just a result that is specifically about randomness. And here I'm using the O+ to mean the sequence that you would get by taking A, taking B, and interleaving them. So you code A on the odd bits, you code B on the even bits. And of course, you can computably separate it out and know exactly what is A and exactly what is B. So von Lembalgen proved in the late 80s that a sequence is random if and only if each of the individual halves is random on their own, but also each of them are random relative to the other one. So for instance, if I have two copies of the same random sequence and I interleave them, I don't get something random. And that makes sense because that would make it very predictable. I could bet on it and I could win as much money as I wanted just by refuse to bet the first time and place my bet for the second time on whatever I saw the first bit to be. And then I refuse to bet here, and then I bet on what I saw the third bit to be. So basically here I would be betting on the even bits based on what I saw on the previous odd bits, which is why we need the restriction that B is not only random, B would be random even if you knew what A was, and of course vice versa. You might also get results about randomness and more classical computability theory. So for instance, Kuchera, I believe the mid-80s again, proved that every Turing degree that computes the halting problem contains a Martin-Luff random. And this was actually very troubling to people for a long time because random sequences are complicated, but that doesn't mean that they should be useful in computations. They shouldn't be able to compute the halting set, because if something is random, you shouldn't be able to access the information in it in any particular useful way. And this led people like, say, Dennis Hirschfeld to conclude that there were two kinds of random sequences. The first kind is the kind that are truly random, and the second kind are the kind that can pretend to be random because they know enough to pretend. An example about, say, local politics. So if, say, in Brazil, if someone asked me very much about the internal politics, I would essentially have to answer at random because I don't know enough. But I suspect that all of you who live in Brazil would be able to also give very random looking answers because you would know enough to be able to get some of the questions right and some of the questions wrong. You would be like the randoms that can compute the halting set. I would just be something that was truly ridiculously random. So, okay, so these are the kinds of questions people ask. You might start by asking questions about how you build a random sequence from another one or two. You could say, in my case, well, we're computability theorists. How does randomness relate to actual computability theory, like the structure of the Turing degrees or something like that? And then, in the past, say, 15 years, people have started thinking more about how randomness could be related to other areas of mathematics. And this result is probably 10 to 15 years old at this point, closer to 10, I think. The idea is that in analysis, most theorems seem to start out for almost all x. So, well, I didn't explicitly say this, but random sequences have measure 1. You only have null sequences that are not random. And the reason for that is this. A random sequence is one that is not caught by a Martin-Luff test. There are countably many Martin-Luff tests because each is defined by a computer program. And each one defines a null class to be non-random. And the countable union of null sets is still null, at least in my book. So so that means that there's only a null class of non-random things, and the class of things that are random have measure 1. So then you could try to relate those classes, these random classes, to theorems in analysis that start out for almost every x. And this is an example. If you have a computable ergodic transformation on a computable probability space, so you have formalized this probability space using computability theory, then a point in the space is random exactly when it satisfies Poincaré's recurrence theorem for effectively open subsets. So in order to relate randomness to analysis, you have to frame the analysis in terms of computability theory, just like you framed randomness in terms of computability theory. And it actually turns out that you can generally do this. You can often say, here's a theorem in analysis that holds for almost every x, and formalize it using computability theory and say, and those almost every x are precisely the Martin-Luff randoms or the Schnorr randoms. So these are the kinds of questions that people ask. Nowadays, people are asking more about randomness and other areas of math. So I think I'll just leave you with a couple of references. The first one is the great gigantic book about randomness that is this thick. And it's an excellent place to start. It's easy to skip around in and read only what you're interested in. And last month, one of my friends and I co-edited a volume about with articles about all of the different directions that randomness has gone in the past decade or so. So if you want to find out more about, say, the first two kinds of questions, Downey and Hirschfeld's book is probably a good place to start. If you want to find out more about the second, maybe the more recent volume might be a good place to look. So thank you very much for your time and attention. It seems remarkably quiet in my headphones here.
Thank you very much, Johanna, for this amazing talk.
Thank you for listening.
So we have already some questions.
Good.
Fabio Cosmo, would you like to talk or should I read?
Well, I just wrote it. Well, let me just say thanks. This was a really, really very nice talk. Thanks a lot.
Thank you.
I'm clapping my hands, but my question is written. So the thing is, sometimes I read that there's controversy regarding the definition of Martin-Luff's random sequence. It seems to me like you're saying there's no real controversy. This is a settled matter now, or is it not?
So I'm not entirely sure what sort of controversy you're suggesting. I mean, so there were lots of different definitions of randomness. Martin-Luff is the one I mentioned because it was the first defined, and it has a relatively straightforward definition in terms of Kolmogorov complexity, in terms of martingales, in terms of test. There are, I believe that some people would say there's an entire zoo of randomness notions. So people could argue about which randomness notion is the most useful or the most natural. So I have definitely heard arguments along those lines. I would personally always start out talking about Martin-Luff randomness, just because I feel it would be much more complicated in a talk like this to start with anything else. But my understanding is that one of the other sorts of randomness, one that I mentioned, Schnorr randomness, where you insist that the measures of the test be exactly 2 to the minus I instead of less than or equal. My understanding is that Schnorr suggested that notion of randomness in part because he felt that that was much more indicative of how people properly think. We don't think, oh, it's less. We don't think about approximations. We say, no, the measure is exactly this. We're much more computable than computably enumerable. I feel like these days people don't have the same sort of argument about this that maybe they used to. I feel that people would say, well, this particular notion of randomness is very useful in this context, this one is useful in this context. It turns out that Schnorr randomness is more useful for instance, analysis, but perhaps Martin-Luff randomness is more natural when you're looking within the Turing degrees. I mean, from my point of view, it's more along the lines of, sometimes I like making pizza and sometimes I like having Chinese food, and they're both very good. It's just that sometimes I want one and sometimes I want the other.
Okay, thank you.
I hope I answered your question. I'm not sure I did.
No, yeah, it was very nice. Thanks. That's all. Thanks a lot.
Okay, good.
Petrus, you would like to talk, or should I read? Well, okay, so I'm going to read.
Okay.
Okay, Petrus asked me to read it. First, he thanks for the talk. And is there another notion of being random? Do some formal notion of being random correspond to it? In other words, there is a kind of church thesis in this theory.
Could you say that again? I want to make sure I understand it properly.
It's in the chat if you would like to see.
Okay.
But,
I think
there's a kind of a formal notion of being random to correspond to it. If there is some kind of church thesis in some kind of sense to this theory.
So I want to say perhaps yes. I've finally opened it up so I can see the chat. I think that the idea of whether there's a natural notion of randomness is somewhat context dependent. If you do, say, constructive analysis or computable analysis, Schnorr randomness will be very natural to you, and the definition will fit very well with the rest of your worldview. If you are thinking about the Turing degrees, so for instance, Martin-Luff randomness might be more natural, but I think there's one in that case that's even more natural than Martin-Luff randomness. And the reason is this. I mentioned, going back, that every Turing degree that computes zero jump contains a random, and some people would say, that doesn't work. I don't want randoms to carry any useful information. And it turns out that there is a way to define randomness. You essentially alter the definition of a Martin-Luff test a little bit, such that the randoms, according to that definition, are precisely the Martin-Luff randoms that can't compute the halting set, so the ones that are computationally weak. And I'm a little bit reluctant to say that there's some sort of Church's thesis notion here, just because when I think about Church's thesis, I feel like every natural approach to computing that anyone came up with gives you basically the same class of randoms. But for randomness, I feel that what people want to say as natural for a randomness notion is going to be very different based on their perspectives. So I think it's going to depend. I think that perhaps the people trained in classical computability theory would give you one answer. The people trained in constructive analysis would give you another answer. So I'm a little bit reluctant to say that there is a Church's thesis sort of analogy here, just on the simple grounds that there are too many different perspectives on what randomness should do for you in a way that I don't believe there are for, say, computation. Does that answer?
Okay, it is. Thank you very much.
Any other question? So it just remembered me of some curiosity, because do you know the R programming language? Probably so.
R, statistics, yeah, a little bit.
Yes. It's made major of these statistics.
I think you just cut out a little, I'm afraid. I'm sorry, I didn't get any of that question. The
Sorry. No, in fact, it's not a question, just something that I remember that in the R language, the developers are majorly statisticians. And they are very strictly to call pseudo-random generators in the language, not random number generators.
I appreciate that.
They call really random. There is just one package. Yeah, there is just one package that many of them, at least, I would not say that most of them, but many of them, what you call random, is that there is a server called to a signal capturing for white noise from radio stations.
Very nice.
Provide your random numbers.
Oh, that's nice. I appreciate it when people recognize the difference between pseudo-randomness and randomness. I mean, I would probably still argue that whatever they pull in from, that this white noise is still only pseudo-random because they're only pulling in finitely much. But that's definitely a step in the right direction. I appreciate that. And thank you, because I do teach my students using R. So now this is another fact I can give them.
There's a page called random. There is just for this command. So if someone has another question, comments. Well, there's a lot of people thanking for the really nice talk in the chat. You can see that. I'm going to stop the recording.
Okay.
But first of all, thank you very much, Johanna. It was really nice.
Thank you for having me.